So, thank you everybody for coming along today to hear the talk. I'll be about 45 minutes, so hopefully a little bit less. But today we are going to look at the subject of beyond dashboards, visualizing complex systems. So a little introduction from myself before we get started. My name is Andy. I'm sure you know that already. I've been here at Skybent and Gaming for the last 6 years. I am lead platform engineer in the infrastructure platform engineering squad. My pronouns are he and him. You can of course contact me through the numerous communication methods internal to Skybent and Gaming if you have any questions on this presentation, but also my Twitter handle is on the screen if you need to get hold of me. Outside of work, for those of you who don't know, I run the DevOps meetup here in Leeds. I predominantly work with Kubernetes technology on a day-to-day basis inside infrastructure platform engineering. And I also help run a conference in London called DevOps Days, which all being well will be happening in September of this year. I mention the DevOps conferences because this talk starts with a talk I saw at a DevOps conference. I was lucky enough to be in San Francisco in 2017. And I saw this talk by John Allspar, who is one of the, let's say, thought leaders in the DevOps community. And he gave a talk about keeping systems running, but stressing the importance on how much we rely on the understanding and the interactions of humans with those systems. I'd advise you to check his talk out, obviously, when this one is finished. But this is one of the slides he presented, and in this slide he's explaining above and below the line, and that we have all our stacks and our systems for deployment, monitoring, testing, and indeed running our applications below the line. And above the line where the humans live, we have all our knowledge, we have our documentation, and we rely very heavily on the abstract concepts of what a system is inside people's heads and in those documents. And he makes the point that that's really important because in reality, this stuff below the line doesn't really exist. At the end of the day, all we've got is electrons going around circuit boards, and there aren't really virtual machines that you can pick up and look at, nor can you, in theory, pick up a database. So the amount of cognitive load and the importance of that is placed on team members is really important. And he makes the point that particularly during incidents, that's increasingly important. This was the other theme of his talk was the Stellar report. And this is a workshop with a load of people from within the industry about dealing with how engineers cope with complexity during incidents. It's a really interesting read. I'd advise you to go and take a look. The thing which I found most interesting was point number 4 about supporting work through improved visualizations. That's always been something I've been really interested in, analyzing and visualizing data. And that kind of leads on to the point of this talk that what's wrong with dashboards? We have lots of dashboards in our organizations, visualizing and showing metrics of our systems and indeed helping us during incidents. So what's wrong with dashboards? And you may kind of imply from that that I'm actually not a fan of dashboards. Well, I am. I love dashboards. I love Grafana. I love a nice succinct dashboard like we've got on the screen here. Very easy to understand, very simple, nothing complex in there. But I think there's a tendency, particularly if you go on the Grafana website itself and look at the dashboards that are available there, that a lot of the dashboards are turning into kind of like live data documents that span several screens deep. And we tend to sometimes cram too much information about those metrics onto them. The graphs here are incredibly interesting, but I'm struggling to understand just by glancing at them what good looks like and what bad looks like. And that can be a problem, particularly when dealing with incidents, and particularly when John in his talk was alluding to creating visualization tools which help people out. I think these are great for showing the state of particular sensors in an application or a system, but what they don't show is they don't show the interactions and the structure of an application. And I think that's just as important as how isolated bits of metrics are demonstrating performance of a system. How do we visualize and how do we show the complexities in systems and the interrelations between the components that make those? And that's one of the reasons I quite like Kubernetes. Kubernetes itself has a bunch of primitives and objects which kind of simplify the building blocks of putting together an application. Obviously, the nuance and the detail is in the actual code that runs within inside these building blocks, but it provides a way of at least consistently structuring and building systems. And I think that one of the interesting things with Kubernetes particularly, or any complex system you've got, is pulling that information and those relationships between the components into something that makes it understandable. And one of the technologies I've looked at previously is graph databases. I'll give you a little whistle-stop tour of them now. At its heart, graph databases are really simple. They're based of nodes and they're based of edges. So in this diagram of somebody's Facebook network, for example, we can see a bunch of people, we can see the relationships between them, and so who knows who within that network. We can see the communities illustrated by the color, and the nodes are sized perhaps by how long they've known somebody. And these were really popular about 10 years ago, and I did some data science analysis qualifications around this very subject. But the main use of them seemed to be for people to put on social media and tweet out with the hashtag data science, which did two things. One, to show off how popular some people were, but also to annoy people who were doing real data science. But graph databases do have their place, and they are useful for applications above and beyond showing off how many friends you've got. Essentially, a graph database consists of two things. It consists of nodes, which are the objects and the relationships between them. Those nodes could have a type, they can have attributes or properties. So it could be a person that has a height, a weight, and a favorite color. And the edges between them and those relationships, and those could be directed. So it could be that somebody likes somebody else. It could be weighted, so it could indicate how much they like that person. And indeed, you can also assign attributes in some systems to those edges as well. And there's a whole science being built called social network analysis around analyzing clusters of nodes and edges to understand the meaning, the interconnections, and the relevance of nodes within the network. And if we think about it a bit more abstract than people or relationships between people, these nodes could be practically anything. They could be people, but they could equally be classes or objects within your system. They could be devices. They could even be data or rows of data, or even like service endpoints in a microservice world. And those relationships could be a linkage between them. They could be a weight, a volume, a usage, or a dependency, or they could be, and as I'm going to demonstrate today, they could be Kubernetes objects and the dependencies between them. And there are a couple of existing tools to help us visualize Kubernetes objects. This one on the left is called KViz. The ones on the right are called WeaveScope and the defunct Cockpit Kubernetes plugin. And all these provide visualizations of segments of the Kubernetes objects that exist in a system, but none of them really show the whole system. They don't show all of the components and all the interconnections of a running system. And I set off to do this in my L&D time. So I'm going to show you what I did. Before I do that, I'm going to go into a demo. It's a video recording. So number one, I won't overrun, and number two, it's got less chance to go wrong, but that's not guaranteed. It does contain a lot of moving images and flashing images. So if you are sensitive to them, then please, you might want to skip the next 17 minutes of this session, because there's definitely going to be some of those in the next few minutes. I keep mentioning Kubernetes, and I realize a lot of people on this session won't know about how Kubernetes works or its structure. So a very quick whistle-stop example. There are a bunch of objects within Kubernetes. So these are all the nodes and their interconnections. Everything is grouped together by something called namespaces, and then we have our actual things that run code called pods at the bottom, and they run on something called Kubernetes nodes, and all the other objects are just kind of workload definitions between the two. So when you're looking at this, if you replace this with maybe objects and relationships between things in your systems, be they data, be they people, be they events in, let's say, a gambling system, for example, if you replace them, then you should be able to kind of see the method behind this and not specifically think about the example that I've shown. So let's have a look at the demo. Right, everybody cross your fingers, this is going to work. Okay, so first example I wanted to show was KViz. So this is a little project which will visualize the Kubernetes cluster which you give it. It's written in something called D3, which we'll talk about later. And this is my little development server on my Mac. This was a really interesting article about pulling Kubernetes into a Neo4j database, which is a big graph database. The author of this talks to the Kubernetes endpoint and uses some extensions to load data, but can load in objects into Neo4j and do some visualization. This is Neo4j. It is got a web browser front end to it. I've started here using Docker. I'm exposing some ports, persisting a folder on my machine so I don't lose the data between restarts, and enabling some add-ons and extras which we'll be using throughout this. But that essentially runs, and we point our web browser at it and we can see data. To get the data in, I didn't use the Neo4j extensions. I wrote some Go code, well, quite a lot of Go code actually. And this loops through the Kubernetes objects hierarchy and finds nodes, the workloads objects I referred to earlier, so deployments, replica sets, stateful sets, and daemon sets. And we'll also find all those pods which are actually doing all the work, as well as the nodes where that workload runs, and indeed the services that connect them all together. So I've already run that because it's not a particularly exciting thing to watch. And inside Neo4j, I've got over 5,500 objects in there and 7,000 relationships. And what I can use inside Neo4j is a querying language, a bit like SQL for those of you that use that. And I can ask it questions. So I can say, find me all the pods and give me some attributes which have come across with the data. And I can even do some aggregate functions on that. So this isn't particularly earth-shattering in terms of relational databases. But what I can start doing is use the visualization tool. And here I'm saying, find me a workload object called deployment with the name of Trickster and show me the things that are connected to it. So here is my deployment with a replica set and 2 pods that hang off it. And I can see all the properties that each of the object has in that little window at the bottom. And I can drag this around and move it, but I can actually start exploring it. So if I expand out the deployment as I've done there, I've got a couple more replica sets which don't have pods because only one replica set has pods. I've got the namespace objects and I can expand out the pods, and I can start seeing where those workloads run on those Kubernetes nodes. And I've also got a service object now. And if I keep expanding this, I can keep on going until I've got practically the whole database there. But then I've got a nice little visualization of one chunk of Kubernetes. Where it's really powerful with Neo4j is I can ask it a generic question. I can say, here is a specific pod or workload I want you to look at, and I want you to bring back everything between it and the associated namespace object. So everything in between. So it doesn't matter what workload objects are between the two, I get them all back. And as you can see here, I can also expand out the objects. I'm pretty much recreating what I had before there, but I can go a little bit further than that. Let's start expanding out into the namespace, and I get lots of objects now. And I can keep on going, expanding the objects as I want. The problem with this particular platform, though, is Chrome struggles to render a large number of objects. So when we get over, say, 1,000 objects, Chrome really starts to struggle. And that's down to, in part, the underlying technologies it's using to do the visualization, which is something called a D3 force layout graph. So let's have a little look at one of those. The D3 library, main contributor is Mike Bostock, and he's put together a bunch of different visualizations, this being one of them. And you can see from just interacting with it, they're very smooth and very visual, and all dependent on the relationships between the data. But it does struggle over a certain number of items. This is another JavaScript library I found, and in this example, it connects to Neo4j and will render with 3D force layout graph. And this is starting to prove a little bit more useful in seeing the whole system. So very simple to implement from the example. You just change the connection for the Neo4j and tweak the query a little. And this took about 5 minutes, one Friday lunchtime. And lo and behold, a couple of minutes later, I had this. And when the animation settles down a little bit, you'll start to see the whole of the Kubernetes cluster and all the things in, all 5,000 objects. And we can drag this around and we can rotate it and we can zoom in and out, and it's all very nice. And I was so impressed with this, I stuck it on the large monitor in our office over lunch, and when my colleagues are back from lunch, some of them were really impressed with that's really slick and that's really cool, and some of them were a little bit more objective and said it's just a hairball. And they're not alone with their opinion of it being a hairball. Martin Jaruski, who is a biochemist analyst, put together this website, really not in praise of hairballs and indeed cluster diagrams like this. Indeed, this particular one is the same diagram but rotated a number of times, and he's very skeptical of the actual number of different layouts you can apply and interpret meaning from them. And he has something called a hive plot, which he believes is a better way of doing rendering large data sets. I decided to use this tool called Gephi, which I'd used when I did some data courses a few years ago. And Gephi is a tool which allows you to visualize large data sets and the interrelationships between them. So effectively a visualization tool for a graph database. And this is Gephi, and we'll see a lot of this now. But if I turn on something called the streaming API, that allows me to send data through a web interface to Gephi, and more specifically from the database I've got in Neo4j. So if I run this piece of Cypher, as it's called, and uses a little add-on, but it finds all the nodes that are connected in the data set and will send it along with all the properties over to Gephi. So that starts to whiz and whir. And as that goes over, if we go back to Gephi, we can see those items starting to load in the window there. They're all the little dots, and in the top right there's a count of how many objects are there, and there are 5,000 objects. So by the power of video editing, we'll just skip forward a little bit, and we've nearly got all of them. It turns out that we don't get every object with that query. There's a few that aren't connected to the main cluster, so we have to run a slightly modified script to do that, to get the remaining objects. So if we do that, we can see it's going to pull everything that isn't connected to the cluster, and that's going to pull across those remaining 16 items we were missing. So 5,567 nodes, 7,234 edges, and there we are, we've got all our data. So in Gephi, we can look at the data as the view of the graph, or we can go and look at it in like an Excel spreadsheet view. And if I scroll through all the nodes that have come across, you will see that the properties that are relevant to that particular type of row are being filled in, and that's all stuff that originally came out of the Go code into Neo4j. So I've now copied that data into there. Now what would be nice is if we give these objects some color based on the type of object. So if we apply that, and we'll just move that across to the other side, make it visible, so we can see all the different object types, including the pods and the namespaces and nodes we mentioned earlier. And if I put this, lay this out, I can use a layout algorithm to draw the diagram using the relationships between the nodes. So that's basically positioning all the objects relative to everything and the other objects in the graph. And what do we get when we get here? Well, we get something that looks a little bit like the thing we saw in 3D. But if we zoom in, we can start seeing all the object types based on the colors on the right hand side. So there's something called a deployment. These are connected to replica sets. These replica sets at the top aren't connected to anything else, but one replica set has got a green dot, which is a pod. And if I zoom out further, I can see that's connected to a service and a namespace. And indeed, the pod itself is connected to a Kubernetes node somewhere in the middle of the hairball. And if we zoom out, we can find it. If we zoom back in, no, it wasn't that one. I don't think it was that one either, but you get the idea. These are connected to the nodes in the middle, and if we select those, you can see all the different pods that run on that particular node, and they're in turn connected to different workloads in the cluster. So if we zoom in here to this interesting namespace we've got at the top with lots of things on it, we can see that we've got lots of objects that haven't got any workloads, and that's why they're kind of at that top edge of the cluster. There's a bunch of statistical stuff built in for analyzing the networks, which I'm not using in this particular example, but there's a ways of filtering the data down to distill what's there. I'm using something called a partition, which lets me filter by the type of object in the database. So in this case, I'm going to filter out the nodes where the pods run. So I'm going to start and look at it from the perspective of workload rather than compute. And if I do that, it takes all the nodes away. And then when I relay it out, I get a very different view of the cluster. I get these isolated little islands. And these are the namespaces with the workloads associated with them. And some of them are very simple, like this one. And I could turn on labels and see what the name is of those particular components inside the cluster. So I can see those names there. These have all obviously been obfuscated to hide them. But I can zoom out and I can start to look around the other workloads and compare and contrast them. I can zoom in and look at this big hairball. I think I'm going to come back to that later and look at it because it's obviously a standout feature of this cluster. But there are plenty of other workspaces to go and look at with different kinds of workloads of varying sizes. So what I'm going to do now is I'm going to look at the cluster in a different way. Rather than look at it from workload, I'm going to look at it from compute. So if I just select the nodes where the workloads execute and the pods, which is what the workload is, I've only got two objects here. And if I relay those out, I get yet another view. And this is showing me all the virtual machines or nodes where the workloads actually run. So I can start looking at things from the perspective of compute. Where it gets interesting is if I start coloring these rather than by type, but by status, I can start seeing the state of those workloads as they run on those nodes. So I might, for example, have a node here that's got a few failed pods on it. Maybe there's a problem with that node. Maybe I should go and look at it. But it gets more interesting when we start sizing as well. So I can go and look at any of the properties that are associated with the object. So in this case, I'm going to choose the amount of CPU an object has requested, and I can size those. And if I lay that out again, zoom out, I'm getting an overview of where all the heavy and noisy users are on the cluster. So I can start to see that we've got actually quite a big workload on that node, and I can turn the labels on and find out what it is, and maybe go and have a conversation or do some analysis on that particular node and work out why it's requesting so much CPU resource. This is another program I wrote. This doesn't use Neo4j, but what this does is it uses something called a shared informer for those that are using the Go API. And I pull out all the individual objects and I create a log file based on time. So I leave this running and it builds up like an event log of things that have happened on the cluster. As you can see, it's quite a lot of information. A lot of it is information about the state of pods, so memory and CPU usage. But as I was going through this, I started to discover some patterns just in the log lines. And I found this particular workload called toggle seemed to be having some problems because there were repeated lines of relationships being added and deleted between nodes. And that was happening numerous times in the log file. So I thought I'd maybe find something interesting there when this was visualized. So the next stage for this is to take this log file and convert it to something that Gephi can read. And this particular bit of code here will read through that log file, and based on the events in it, it will create a graph for me, which I can load into Gephi. The interesting thing about this is what I've done is I've marked little time intervals of when objects are available and when objects are not available, so like their lifespan. So if I pull this into Gephi, it lets me do something really quite powerful. So there's our graph exchange file. I pull that in. And you can import things into Gephi using CSVs or any data format really, but so far we use Neo4j and this GAFX file. Again, I'm coloring the nodes as done before. If we look in the data laboratory at that view, so the Excel kind of view, you see there's an extra field now with intervals in it. So this is when the object creates and when it's destroyed. So it's how long it's valid for. And at the bottom, after we laid it out, let's just lay it out first. Okay, familiar shape. At the bottom, there's a big button saying enable timeline. So what that lets us do is it lets us treat this file as almost like a recording of the cluster's lifespan. So I can change this little time portion of the cluster so that I can then drag it around and I can see the cluster change over time. Here I'm resizing the nodes by CPU metric, and I've applied that. And if I hit the play button to go through the timeline, you can see the objects in the middle changing size, indicating the state of the cluster at any point there. And that's really important because it gives us like a point in time view of the cluster, which might be handy in an incident. So kind of like a black box recorder. I'm now going to go and find that pesky toggle thing, which was bothering me before. So if I find it and select it on the overview and go back to the overview, I can see on the left hand side there's the toggle node there. And if I resize this window and drag the head along, I can start seeing a flashing green line on there. Yeah, so from this node here down to one over here, and as I drag the playback head, you might be able to see a green line appear. So this green line here, so that's appearing and disappearing as we go through time. So it indicates there's a bit of a problem with that particular service and something to definitely check out. Now what I'm going to do here is I'm going to arrange all the nodes into a circular layout with the edges between them. And if I enable the timeline and choose a chunk of this, and this is a different data set, by the way, this is like a Monday morning when it's when the cluster is really busy. And what I can do is if I just hit play or scroll along, I can see the workloads starting to appear from the edges of the cluster and joining the bits of the cluster they relate to, which is kind of useful. It's probably more useful if we look at it by workload or by compute. So this is the same thing again, but this time I'm going to use the filter to partition out the nodes. And this time, if I run the layout, I can see all the individual workloads. And as I hit the playback, you will see all the workloads flying in from the edges and joining the relevant namespace where they belong, which is kind of cool, but it's also quite useful. And for completeness, let's do the same from a compute perspective. So here I've done the same. I'm now going to filter it out by pods and nodes so that I've only got those particular object types there. And I'm going to hit the arrange and play. One thing to look at as this this animation comes along, there's an area just about here where my big mouse pointer is, where we're actually going to see a node being created. So we've actually caught a node being added to the cluster and then the workloads joining it. So there it is, and the workloads join it. So we can see where all the workloads are heading up. So that was a little bit of the demo. Hope you found that that interesting. Let's get on with the rest of the slide deck now. So graphs or hairballs. We've seen a couple of different ways of looking at workloads and animating them and getting meaning out of them. Let's have a quick recap of the tooling we looked at. So Neo4j is a enterprise level database. It supports ACID transactions. It's scalable. It's highly available, and it is a paid for product, although there is a community version available, which I used in this demo. But it's one of the few kind of commercially supported graph databases out there. Gephi is an open source tool which allows visualization of data. I'm particularly fond of the layouts, the dynamic filtering, and the time-based element to it to do visualizations. There's a bunch of layouts listed there, and you can add many more through the plugins option. And it does have, although I haven't used it, a bunch of tooling around graph theory and social networking analytics. So looking at paths, so where things sit in the network relative to one another, the importance of nodes in there, so their centrality, and identifying communities. With the data set I've got for this, with them all being of different types, that wasn't particularly useful, but I'll quote an example of someone that's used something like that for another purpose in a moment. Before you all run out and download Gephi, just some words of warning. This is the wonderful team that have been helping make Gephi happen for the last 10 years, but they're quite open about its future. They've given talks at FOSDEM and indeed on posts on their blogs about where Gephi is going to go next and what design decisions they're making about it. So think carefully before deciding you're going to use it in anger for everything. It can be a little quirky, and there's a bunch of resources at the end of this presentation that will explain how to get started if you want to start using it for your projects. We spoke about hive plots briefly by Martin, who put the website together against these hairballs. We don't have a hive plot in the current version of Gephi, but we have something called a radial graph, and I'm not sure, given this data set, how useful it is, as you can see, but I'm sure on maybe smaller data sets there's a lot of value in it. In terms of technologies to use in the future, I'm certainly going to start looking at D3. I did kind of say it struggled with very large graphs, but I think if we can distill the information down in there, it's got so many different ways to visualize data. It's certainly a tool I'm going to be looking at. There's the Observable HQ website as well, which is kind of like a Jupyter notebook, but for graph visualizations done in D3. That's really interesting to go and look at examples. One of them is a parallel coordinate graph, which is in the bottom right. This data on here is actually the pod data extractor for Neo4j, and it lets me compare the pods on a number of different axes and dimensions, and that proved quite useful as well. So what did we find out from analyzing all this? What were the takeaways? Well, we did a lot of analysis on the test clusters. The live servers are very well maintained, but fortunately, being Skybet in gaming, we encourage a culture of experimentation and collaboration, and we found some interesting anomalies which were sometimes things that we needed to help people with, but sometimes were our own doing. Let's have a look at them. So the first one was this pretty diagram, which I actually got out for Neo4j. This was one of the first renders I took, and we can see all these large yellow objects made up of all these small yellow dots, and what they are is the replica sets. And what it demonstrated was that normally there should be 10 of these yellow dots around each of these deployments. There are obviously quite a few more, and when we dug into looking at how certain workloads have been configured, we discovered that someone had turned the history limit up to 11, which meant that that was going to keep getting bigger and bigger. So fortunately, we were able to talk to the teams which were doing that, and that's no longer a thing. But even by doing some simple analysis, we found out something from the cluster. In Neo4j, so not even in Gephi at this point, we are doing some interrogation of the services in the cluster and finding out straight away that we've got a load of service objects that don't point to any of the workload objects, don't point to pods. That could be a problem, so we can go and have conversations with teams about those objects. If we start sizing the workload objects, the pods, by CPU and memory, we can not only find out where the noisy ones are, but we can also find out if they're connected in any way. Maybe there's a certain workload which is being much noisier collectively than just isolated ones across the cluster. So we can find that out. Sometimes the API lies to us. Apparently these two pods wanted 1 million terabytes of RAM. We don't have that much. I only wish we did. Instead, it was actually 1.2 gigabytes, but the API sometimes lies to you with its numbers. And I did some work to split this in two. So I split the hairball and I suppose the head of this particular graph into two and did some analysis. And what was really interesting with this was what I thought was going to be a really complex namespace, namely that head. If we took all the unused items off it and simplified it down, it was actually a really well maintained and managed namespace with things that were span down and span up as they were needed. Whereas the main hairball, even though did a lot of work to distill that down, it was still a hairball at the end of the day. Here's a view of the active bits of the graph. So, and these are sized by age. And if we filter these down using the partitioning tool and just look at replica sets, we can see there are some kind of big dots there, which indicate they may be quite old. And having a whole old replica set means we might have some old pods, which may have some out-of-date code, which might have bugs or some security risks with them. So we can then go and talk to teams about the age of their workloads and maybe they need refreshing. This graph indicates the number of restarts of these workloads, so if they're failing and restarting, and we can already see that there's a node which may be the source of trouble here. It might not be, it might be the actual workloads themselves, but we can go and talk to teams about those workloads or do some analysis on the node where they run and understand it better. On this particular one, we're sizing and looking at the status against those nodes again. So we've got workloads which are being greedy, and we've got workloads which are regularly failing. And interestingly enough, on the side here, we've got some pending pods. So these are pods which haven't been scheduled onto the cluster yet. Now that might be because this is just a point in time when we took the data, the snapshot of that, and they may have been happily scheduled, but we can go and find out how long they've been there. And if they've been there a while, it might mean we've got some issues on the cluster that's preventing workloads from being scheduled, or some workloads, and we can investigate that as well. And this is much the same view, but by a workload view, so looking at it on the namespace, so we can see if any of the namespaces have actually got some problems with their workloads failing or being rather large, and indeed it looks like we have. So again, we can go and look at that. Sometimes Gephi mocks me. At the top here, there are 3 nodes, and the pods around them have quizzically repositioned themselves in question mark shapes. I spent quite a lot of time trying to work out why these 3 nodes were different to all the other nodes in the cluster, only to realize that they were our control plane nodes, which actually run Kubernetes rather than the workloads themselves, which was a bit annoying, but lesson learnt. And the other lesson learnt is when you see an anomaly, think about it before you go running off with screaming that the cluster's on fire, and also make sure you pay attention at stand up. It could be that one of your colleagues is load testing a node and you just didn't realize or pay attention. Whoops. Okay, what can we do next with this? Well, we could do more or different Kubernetes objects into the cluster. We could look at how storage is being used. We could look at the security rules and the permissions across the cluster. And we can look at more real-time data as well by pulling that out of maybe the monitoring system as well to enhance that real-time view. But the really obvious one is looking at networks and the connections between things in the cluster and each other. So by analyzing the network policy objects, so they're kind of like the firewall rules, the different network connections or services, or indeed in the service mesh that glues over the top of all the workloads, we could probably work out some really interesting stuff. And I'm not the first person to have thought about doing this. This is Jack, who works at Monzo, who posted this back in November. And I had a little chat on Twitter with him, a few DMs, as we have a mutual friend, and he was explaining that they were just really analysing sets of static rules they had, but equally, they may well be doing something a lot more interesting now, but that was rendered out in Gephi as well. And then just this Wednesday, I came across this talk by Nikki Watt, who's CTO at OpenCreode. This was from GoTo Berlin, and she's talking about how to use those social network and graph theory tools to analyze interactions between microservices and optimize them. It's a really interesting talk, and it only came out on Wednesday. So in summary, what have we learned? What have we done? How do we wrap this up? Well, I am, as you probably guessed, a big fan of DevOps. I'm a firm believer in getting rid of that wall between dev and ops and working together and collaborating on stuff. If you read the book about doing such a thing, Team Topologies, which Sky Betting Gaming are in, I would add, they identify 4 different types of team. In infrastructure platform engineering, we already have created an enabling team, which I'm part of, to do the DevOps thing. And we're certainly using some of the learnings from this L&D that I've been doing to improve our collaboration. Have we solved this problem about improved visualization? Well, maybe locally, yes, but maybe not at a broader level. But what I have learned is what people are using our cluster for, and what I expected to see on there was nothing like I found. It's been really interesting and in some ways reassuring to see how teams are using our cluster and the understanding. I think the real power of the tooling is going to come as we enhance the kind of black box flight recorder and be able to play back the state of the cluster at various points. I think that's going to be really interesting. And although that's not become a formal thing, I think a lot of the ideas and things we found out through analyzing the cluster and the data, and particularly in terms of usage, is really starting to bubble up in our approach to talking to teams and what we're prioritizing working on in terms of the collaboration aspect with teams. If I was going to give any advice about analyzing clusters, analyzing hairballs and graphs, it would certainly be to kind of accept that you're going to have hairball. The complexity in a complex system to me is symbolized by that hairballness. But if you can remove as much noise as you can and start thinking about a perspective to apply context to. So if you think about looking at just the workload bits or just the compute bits of this cluster of nodes, you begin to understand a lot more reasoning of it. And if you can expand that, as we hope to, with looking at connectivity and indeed security and combining those perspectives, there's certainly some very strong lessons that can be learned and found there. I say just one more thing, just two more things. Firstly, thank you for spending some time this afternoon watching this presentation. Appreciate you taking your time out of your day. Hope you've got some inspiration, and even if you don't use Kubernetes, you can kind of map some of the techniques and learnings to objects or entities which you work with, and may be able to start using graph databases and visualization tools to get some real meaning out of them. The other thing is that the resources for this deck are in this next section, and I'll whiz through them quickly. Here we've got links to all the different tools and all the different bits of tech that we used in the making of this. I will be adding links to the bits of Go code as well when I have a home to put them. So I will be supplying this deck with some screen grabs from the videos in, and I do hope you found it useful. And I think we've got a little bit of time to do some questions and answers, but with that, thank you very much for taking the time out for the day to watch the presentation. Thank you very much.